Another variation of a sine graph involves a graph that has a basic look of y equals amplitude times the sine of another constant times x. Now we've dealt with what the amplitude does. We know that's the stretching, the vertical stretching factor. Now variables are coefficients in the x within the function, as b is here. What that will do is vertically stretch or shrink horizontally stretch or shrink the graph. Amplitude up and down, inside the function where this b is at, left to right. And when we'll do that is we'll look at some examples. One, we can identify the period, the amplitude, but the period will change a little bit. With a sine graph, the basic period is 2 pi, but we are going to stretch or shrink that by a ratio of b. And that will take our normal graph and extend the period to 2b divided, or 2 pi divided by b. So let's look at an example of how that would play out. So again, the example that we have, or the example we want to look at is, let's graph y equals 3 times the sine of 2x. Now we're already familiar with the sine curve. We know what the amplitude is. Amplitude is a 3. So I have my graph marked off 3 high and 3 low. We know there's 5 key points along the graph. There are key points that we want to look for in our x values. But to find those, we need to determine what is its periodic checkpoints. The period of a graph is determined by 2 pi in a sine graph, its period, divided by the value of b. So in this particular case, I would have, where's my graph going to go? I would have 2 pi divided by b, in this case, which is a 2. So I have a full period taking pi to travel. What does that mean? It means that my first point here would be 0. My last point, rather than 2 pi's normally, it's going to be a pi. That's how long it takes to go a full cycle. Then from there, I divide that up into 4 chunks. And every 4th chunk is going to be, so this first point is going to be pi fourths, then pi halves, and then what is that, 3/4 pi. So those are where my 5 key points will be at. From there, I'm going to input the 5 values in there to get the nice, smooth, continuous curve. So 3 times the sine of 2 times 0 is 0. 3 times the sine of 2 times pi fourths is a 3. Pi halves will produce a 0. 3/4 pi will produce a -3. And then back to pi, it will produce a 0. Those are my y values. Then we draw a nice, smooth, continuous curve that goes through those points. So notice something on this one. It may not look like it on our scale of our graphs if we stretched or shrinked along the horizontal axis. We can see it on the vertical axis that we're up by a factor of 3. We notice that. But the stretching point, notice that my full cycle completes at pi. If I were to do the normal y equals sine graph, maybe this will help with comparison. The normal y equals sine graph, first of all, has a maximum at 1, not 3, because it's just there. So, and that occurs at the point pi halves. Then back down to 0 at pi. So that's the start of the normal pi or y equals sine graph, and it will continue on and work its way back on up. So do you see the differences here? Maybe from this you can see then that the 2 does congest or shrink, unshrink, unstretch along the horizontal axis, so it completes a full cycle by the time it reaches pi. The normal graph, it takes a full 2 pi to reach a normal cycle. So because of that, we can see that the graph has shrunk. And that's a good idea. Every time you graph one, graph on top of it y equals sine of x, so you have a better idea how it's changing vertically or horizontally.